and then progressively move to more complex systems, all the way up to a dissolving electrode that we've been studying. So more specifically, I'll start off with the silver 100 system and explore what is needed to capture the capacitance features of the surface in aqueous non-interacting electrolyte to really understand the double layer structure of the surface. Then next, I'll move to a slightly more complicated system, the platinum 111 surface with a CO add layer, to explore what dominates its capacitance, and of course, how this differs from that of the silver. And then lastly, we'll look at copper 100 with a C2x2 add layer of chloride and explore how dissolution occurs on this surface. So starting with the simplest idea of the electrochemical reaction environment, we can consider an electrode with some surface charge sigma, and the surface charge is canceled out in the double layer. And it would be really nice to be able to identify what the charge on the interface is at a given potential. But of course, it varies with potential and with local chemical environment at the surface, depending on the solvent, the electrolyte, adsorbates, and diffusion and other reactions that happen. But in general, the charge at the electrode at a given potential is the integral of the capacitance from the potential of zero charge all the way to the potential of interest. So of course, the differential capacitance is then the change in the charge with the change in potential. But an easier way to think about this capacitance would be to model it as a capacitance in series with different capacitors along the z direction in this sample electrode. And so the inverse differential capacitance then is the sum of the inverse capacitance of each capacitive element. So to give you an example, moving back over here on the left, one can think of the first capacitive element is most likely going to be the quantum capacitance of the electrode. And if this is a metal, this value will be really high. This means that the inverse will be really small, and this quantum capacitance of the metal isn't going to dominate the differential capacitance of the entire system. So the point here just is we need to figure out what capacitive elements dominate the capacitance at a given potential, and we need to make sure that we model those correctly. Now, of course, this is a really tricky problem. Modeling the electrochemical environment requires understanding the configurational entropy of the electrolyte. We need to consider the fact that the charges are mobile, and the fact that for these types of calculations, we are interested in the fixed potential values. So given that the electrolyte and the surface electrification cause significant modeling challenges, we developed continuum models to neutralize the cell and to provide the electrolyte environment and to understand what is happening in the double layer. So more specifically, here we are using plane wave DFT calculations from JDFTX. And by the way, this is an open source code and freely available to everyone, available at this link. And we developed these dielectric continuum models to describe the double layer, and we use the DFT calculations for the electrode, for the adsorbates, and for the things that don't require any motion of the electrolyte. So specifically, the goals for this continuum modeling are to develop continuum models for use in hybrid continuum ab initio calculations, but also to understand the physical characteristics of the interface necessary to accurately model these long-range electric fields. So when we started this work, we developed a number of very simple solvation models, and others did as well. And these basic models had the following elements. We have a metal that we describe with DFT, and then we have a gap region. So as the electron density of the metal decays exponentially, at some point we hit some electron density threshold, N sub C, and at that point we turn on the dielectric continuum with ionic screening. This continuum model is generally uses a dielectric constant, a single value. And here, for instance, this is for water. And we have an ionic screening component as well. And when we first developed these models, we benchmarked them against the solvation energies of ions and molecules. but we also needed to benchmark against the capacitance of aqueous interfaces. So the very first benchmarking that was performed for these types of solvation models happened using the platinum 111 differential capacitance, which I show here on the right. And so you can see that the capacitance at low potential starts out as incredibly high, and then it dips down, and then it rises back up again. And the capacitance on the left is nearly as high as 600 microfarads per square centimeter. And this is a huge capacitance. And it turns out this isn't actually just the capacitance. This is also the pseudocapacitance associated with the hydrogen evolution reaction happening on the platinum electrode. So we don't actually know what the true capacitance of the platinum, or even the platinum with the hydrogen, is at these potentials. Then we move to a lower region, which has been characterized as the double layer region, but it still has fairly high values. And then we continue moving to the right, and we can see very large values yet again, and this is associated with the oxidation of the platinum 111 surface. So as you can see, the platinum 111 isn't a particularly good benchmark, but it was still what was used originally because people believed that the platinum 111 double layer region was relatively perfect. So the experimental capacitance value is around 20 microfarads per square centimeter. This is only an estimate because of the limitations, the experimental limitations, and one can see that all the solvation models fall within the same order of magnitude for their capacitance estimates. But this is, of course, very limited because we only have a comparison of a single value for the capacitance. So after looking through the literature, we discovered that the silver 100 system would be a much more appropriate system to benchmark against because it appears to have very idealized behavior throughout the entire capacitance curve. So one can see that it's a very symmetric curve. It's symmetric against the potential of zero charge. And as one moves to the left, the surface is negatively charged. And so positive ions, such as the potassium, interact on the left side. And on the right side, the surface is positively charged and has negative electrolyte interacting on this side. And the symmetry implies that there is no specific binding to the silver 100. Additionally, we can see that when the ionic concentration is varied, the capacitance dips as the concentration is lowered. And this is standard Gouet-Chapman behavior, and this provides further evidence that this is an ideal electrode and an ideal electrolyte. So it has no specific binding. So with this very idealized system, we can now study the existing solvation models that have been previously developed. So we can see the experimental data shown in black, and we can see that when we compare against the results from our solvation models and the solvation models developed by others, we have incredibly poor agreement with experiment. It is qualitatively incorrect. I'd just like to mention also that there's a large peak here in the candle capacitance curve. And this is an unphysical peak, and it is caused by the fact that the solvation cavity expands when the surface becomes negatively charged. And so this doesn't reflect anything that is seen experimentally. Even when we reparameterize our solvation models, we still cannot even qualitatively reproduce the experimental capacitance curve. So clearly, once we realized this, we realized that we needed to develop more sophisticated models to capture this capacitive behavior. So we considered a number of different components, and we wanted to identify which capacitive components are necessary to accurately describe the silver 100 capacitance curve. So we started out with a model that included a metal, this X1 gap region that I discussed earlier, where we turn on the solvent once we reach a critical threshold, low threshold of the electron density. And then we include a second gap where the solvent can access, but the electrolyte cannot. And this is something that's included in a standard Gouet-Chapman Stern model. Essentially, due to the fact that the ions in solution are hydrated, and the hydrated ions can only come so close to the metal surface. Then we also consider the third region, which has the solvent and the electrolyte, but rather than just including a dielectric constant with a single value, we now consider the dielectric as it changes as a function of electric field. So to explain this nonlinearity of the dielectric just a little bit more, we can imagine we have some solute, some cavity, and when we charge this electrode, the solvent responds to the charge on the electrode by rotating. So in this example, this is of course water. So the water rotates in response to this field, but it can only rotate so much before eventually saturating. So now we can consider this figure on the right. We can see the relative permittivity as a function of applied field, and we can consider a bulk fluid, so bulk water, using classical DFT, and we can see from the plus signs that the dielectric constant does not remain around 79 for water for very long as more and more field is applied. And we can model this behavior using nonlinearity of the dielectric, literally just assuming the saturation of the rotational response of water, and we find very good agreement with the classical DFT. This strongly suggests that this nonlinear model is very important when the electric field becomes large enough. However, I'd also like to note that others have considered one other physical possibility for limiting the response of the fluid, and that is the packing limits. So in a normal continuum fluid, the packing isn't constrained by the size of the ion. So in a real physical example, of course, the local concentration of the electrolyte is limited by the hydrated size of the ion. So here I show potassium. The potassium can only pack to the concentration of the packing limit of the potassium, which is related to the 3.3 angstrom hydrated radius. So the size of the hydrated ion limits its local concentration when the modified Poisson-Boltzmann equation is used. So it is unclear how important the packing limits are relative to the nonlinearity of the dielectric for the specific case of water. Fortunately, though, we can provide a comparison to sort of understand the importance of the modified Poisson equation and to understand why the packing limits and when the packing limits might be important. So on the left-hand side, just for reference, I'm showing the nonlinearity of the dielectric, and on the right side, I'm showing the contribution of the modified Poisson-Boltzmann. And one can see, if we consider the Debye length as a function of relative potential, the Poisson-Boltzmann equation fits relatively well up to a certain point, at which point the modified Poisson-Boltzmann equation becomes necessary, because now the local concentration of the ions is too large and needs to be constrained. So essentially, packing limits do become important at very large potential differences. So in 2019, Mazzari, Andreucci, and Dabo published a paper suggesting that the packing limits were responsible for the capacitive behavior of the silver 100, and I'd just like to briefly discuss this in a little more detail. So from the literature, one knows that the potassium hydrated radius is 3.3 angstroms, and the ionic radius is 1.5 angstroms. And so if one constrains the local concentration to 2 molar, then this is associated with a hydrated radius of about 5 angstroms. And for 20 molar, it's 2.3 angstroms. So one can see that the 20 molar is closer to the hydrated radius of the potassium. And so if we look on the left figure here, we can see the experimental capacitance shown in dotted lines, and we can see the capacitance if packing limits are enforced, but the nonlinearity of the dielectric is not considered. And one can see for both the 20 molar and the 2 molar values, the packing limits must be set to unphysical values to qualitatively agree with experiment, and they still don't completely agree with experiment. So in comparison, when we consider the nonlinearity versus the packing limits, once again, here I have the experiment shown in dotted black lines, and the solid black line shows inclusion of every single model effect that we considered. So we have an X2 gap, we have an X1 gap, we include the nonlinearity of the dielectric, we have the modified Poisson-Boltzmann equation, and one can see from the black line that if we include all of the effects, we have fairly good agreement with experiment. However, we can remove each one of these effects and see how much they matter. So if we remove the X1, we can see that we do not have qualitative agreement anymore. The same thing applies for the X2. Yet again, this applies if we do not include the nonlinearity of the dielectric. However, if we don't include the modified Poisson-Boltzmann, so the constraint on the concentration, we can see that the agreement is still fairly good. So the nonlinearity of the response of the water qualitatively accounts for the double hump behavior of the aqueous silver 100 electrode. However, this model has not been widely applied yet. Here, I illustrate a number of the linear response and nonlinear response models, continuum solvation models that have been developed over the last few years. And the vast majority of these do not have a nonlinear dielectric. There are only 2 models that have the nonlinear dielectric, and out of those 2 models, only one of them has a non-zero X2. Our NIST solvation model that we developed in 2018. You can see more in our review paper for further discussion of this. And all of these other solvation models are not expected to qualitatively agree with the silver 100 capacitance data. So despite the fact that we understand how to model the silver 100 capacitance curve, it is worth mentioning that there still remain a very large number of continuum modeling challenges. One of those challenges is the fact that electron redistribution occurs. So Jun Chang and his co-workers published a paper in which they demonstrate that the water and the metal, in this case a platinum metal, interact chemically with each other, and the electron redistribution happens across this X1 region. And continuum models cannot describe this electron redistribution, at least not at this point. A second caveat pertaining to continuum solvation models is the fact that there are known explicit interactions with cations, as Karen and coworkers have also shown. In this particular example, I'm just showing the cation dependence of the peak potential of a platinum step edge peak as one desorbs hydrogen and adsorbs OH and water and an explicit cation. So behavior such as this cannot be captured by the continuum models, so it's important to understand what regime one is in so that one does not apply continuum models in places where it is inappropriate. And then lastly, as I discussed with the candle model at the beginning, one needs to define a cavity, and this cavity shape, this X1 and this X1 size, is known to depend on the field and the surface charge, but the functional form of this dependence is not yet known. And additionally, we describe these cavities for the most part as local, and this obviously isn't true. Water molecules have a size, and they have a shape, and so understanding how to define the cavity shape in a more sophisticated way would further improve the continuum models and is a large existing problem. So despite the number of challenges that continuum models still face, they can still provide us with plenty of insights. So here I moved to the platinum 111 system with a CO adsorbed on the surface, and we once again consider the differential capacitance and the various capacitive elements in this electrode. So of course we have the capacitance of the metal, we have the capacitance of the adsorbate across the CO bond, we have a gap capacitance, and then we have the capacitance of the liquid and the ion. And we found in this paper that the gap capacitance of the platinum CO ends up being the dominant contribution of the capacitance. So just to briefly illustrate that, here is the inverse capacitance as a function of distance, a z distance away from the metal surface. And we can see first for the platinum 111 system, without the CO adsorbate, the capacitance drops across this gap region, and that's all that happens, versus on the platinum CO, one sees that the metal capacitance is very large and so doesn't contribute much towards the total overall capacitance drop. Then there's a capacitance drop associated with the adsorbate, and then a very large capacitance drop associated with a gap between the O and the beginning of the water. So the CO on platinum capacitance is dominated by this CO solvent gap. And this is very interesting because it wasn't clear before this work was done whether the majority of the capacitance gap actually occurred across the CO bond. Instead, this is a story of the hydrophobicity of the system. So now changing subjects to discuss the third topic, the dissolution of copper 100 with C2x2 chloride. So first I'd like to mention that corrosion damage is responsible for approximately 3% of global annual gross domestic product. And if we could find ways to decrease the amount of corrosion damage that happens, we could potentially save vast amounts of money and resources. Specifically, it would be crucial to understand corrosion mechanisms to extend infrastructural lifespan, to let bridges last longer, to let implants last longer, and specifically to develop corrosion-resistant coatings and alloys. And both of these strategies are needed, even though here I focus on coatings. And this is driven by the fact that there are a number, that corrosion is ubiquitous, and there are a number of applications in which corrosion needs to be mitigated. And many of these applications of corrosion involve large amounts of infrastructure. And so developing perfect corrosion-resistant alloys isn't sufficient to solve the problem, because sometimes for like a bridge, you need to have low-grade steel and you need to develop some sort of coating that can make these materials last longer. So corrosion is a very difficult problem, and if we had a test system to understand corrosion, it would be a whole lot easier than if we were trying to look at a system where the end product is degraded and the surface structure is no longer apparent. So one toy example is 100 surfaces with C2x2 add layers, and these are actually quite common in both ultra-high vacuum conditions and in electrochemistry. For instance, sulfur, iodine, bromine, and chlorine all exhibit these types of patterns under a number of conditions. So on the left here, I show an STM image of palladium 100 with a C2x2 add layer of iodine. And if we consider the atomic structure, one can see that the halide sits at the hollow sites of the 100 metal surface. Under potential control, something rather extraordinary happens for the palladium 100 surface. So here in the solid black line, I show a voltammogram of palladium 100 and without the presence of iodine. And one can see that under potential control, at low potentials, nothing happens. And then there's a small peak associated with the oxidation of the surface. A protective oxide layer forms, and nothing else happens to the electrode. This is reversible and clean. However, in the presence of only a monolayer of iodine and effectively no iodine in solution, as one increases the potential, instead of the protective oxide layer forming, the surface dissolves. This is, of course, not reversible, and is rather extreme. In fact, it is even more interesting because it happens in a layer by layer fashion. And this is believed to happen at the step edge. So because of the importance of the step edge, it's important to understand what happens to step faceting in the presence of these C2x2 chloride structures on copper. So here we start with a clean step edge. There are two different types of step edges on copper. There's the S1 type and the S2 type. The S1 type is along the 100 direction and the S2 is along the 110. And one can see that these differ and that the S1 is straight and the S2 is kinked. This kinking causes very low coordination on these half of these edge copper sites. And this is extremely energetically unfavorable. So without the presence of chloride, the S1 is favored. However, in the presence of chloride, the situation changes, and the chloride preferentially stabilizes these sites, and now the S2 type structures are much more stable. And this is known experimentally. On the right side, I show the S2 steps that have been shown in STM images in the presence of chloride. However, the situation is a little more complicated in the presence of chloride because there are multiple possibilities for where the chloride can sit next to the step edge. There are S2 type steps where the chloride is relatively close to the step edge, but the S2 type step constrains the perpendicular S2 type step to an S2 prime step because the chloride can now, because of the way the lattice is structured, the chloride can no longer sit as close to the step edge. So we have S2 type steps and S2 prime steps, but we could also imagine putting a chloride in between on those sites, and that becomes the S2 prime plus chloride. So the step fastening of these vicinal surfaces changes in the presence of chloride, but as you can see from these images, the dissolution is incredibly orderly. So it's much easier to study with a chloride add layer than the bare copper case. So a brief discussion of the methods, because they're slightly different than the continuum methods that we applied earlier. So we have a number of DFT systems, and then we use the DFT to develop machine learned potentials using the Baylor Parallel Neural Network from N2P2. And then we put these potentials into lamps so that we can optimize the structures. And I'd like to note that this is preliminary work, so at this point we haven't included a double layer yet, and this is only the uncharged surface, and including the double layer in the system right now is intractable for us because the surfaces that we are looking at are very large. And of course, this is continuing work, and we plan to include Solvation as we learn more about these systems. So now I'd like to show you the DFT results for the step edge formation energies as a function of potential. And one can see, looking at the convex hole, that first the S2 prime is the most stable, followed by the S2, followed by the S2 prime plus chloride. So this is exactly what is seen in the experiment. This is a very good sign that the DFT and solution, that the DFT can approximate the experimental results, even though we don't have explicit solvation. Next, we consider this exact same system using our neural network just to test and make sure that our neural network has been developed in an accurate way. And we find incredibly good agreement for the step formation energies between the DFT and the neural network. So this confirms that the neural network is probably a very good choice for us for looking at larger systems. However, we do one more comparison, and we explicitly compare against experiment to explore the exact step structure, the positions of the chlorines specifically. And this had not been previously known because it's very difficult to take an STM image and to actually understand where the edge atoms lie, because there are so few of them. So here we have the chlorine height profile as a function of distance for the experimental STM images, that's shown in blue, and then we compare against our neural network results, shown in black, and we can see that we can actually correctly identify the step edge structure of the chlorine. More specifically, we find that the chlorine set and the threefold hollow at the step edge, rather than the S4, the fourfold hollow at the bottom of the step edge. And this is true for both the S2 type structure and the S2 prime structure. So this is a very nice application of the neural network results, because it allows us to look at multiple structures that are too large to easily optimize and randomize with DFT. So then, continuing with our neural network, we can also consider the dissolution of the copper 100. So here we have a test step edge. We have an S2 step on one side and the S2 prime on the other step, and we can make a heat map of the removal energies. So effectively, we just remove one chloride from one copper from the system, and then ask, after it relaxes, what is the energy of the overall structure? And so we can sequentially remove every single atom along the step edge to identify which atom has the lowest copper removal energy. And we find, just like we expected, that the layer by layer dissolution mechanism promotes dissolution along these kink sites. And this becomes more interesting because now we can consider any structure that we want, even those seen from experiment, and identify which atoms are most likely to dissolve first due to their low removal energy. And so basically, we now have a model that can predict the layer by layer dissolution of the surface. And we plan to continue this work and understand in general how charge changes this picture, because we know that at this point, the results might be limited by this fact. However, though, the neural network successfully predicts the energetics of the dissolution of the system. And also, we have a model for the dissolution behavior of these step surfaces, and we can predict step structures, and we can verify with experiment. And we are really looking forward to applying this to more complex systems. So in summary, we considered 3 benchmark systems. We first considered the silver 100 and asked what is needed to capture the features of the aqueous portion of the double layer. And we found that the linear continuum models such as VASP, SOL, and those in Quantum Espresso do not correctly capture the capacitance behavior of this metallic interface in aqueous solution. And further, know that a continuum model suitable for electrochemistry, or at least suitable for electrochemistry if you need to accurately describe the capacitance of the double layer, requires at least nonlinearity in the dielectric and ionic responses and a non-zero X2. We then explored the platinum 111 system with a CO model layer and found that the gap region dominates the capacitance of the system. And then we considered the copper 100 system with a C2x2 add layer of chloride, and we found that we could identify where the chloride sits on the step edges, and we could develop a model for the dissolution, and we were able to confirm that dissolution occurs at the kink sites at the step edge intersections. So I'd just like to thank you all, and especially thank all my collaborators. It's been great working with everyone, with Shankar Sundararaman, Kendra Letchworth-Weaver, Mark Coper, and Mitchell Grenenboom. So thank you.
Okay, thanks so much, Katie, for that really interesting talk. And so now we are open for questions. And so participants in the audience, please either type your questions into the chat window, or if you'd like to be unmuted to ask your question live, just type an X. Okay, so. Okay, so would you like to? Okay, yeah, Nitish,
Sure.
I mean.
Yeah. So the first question's by Marco Miranda. So he says, thanks for a nice presentation. I have two questions regarding the solvation models. Do you expect that the effects of charge transfer between the surface can be captured between the surface and the solvent, I guess, can be captured with implicit models? And what is your perspective on the best practices for parameterizing solvent models for surfaces?
Okay, so hitting the first question, so implicit models obviously now don't capture the charge transfer, and this obviously is important because it considerably shifts the PZC. However, first of all, it is unclear how much this changes the capacitance in series. And second of all, it might be possible to develop a continuum model. It might be possible to develop a model that includes continuum model aspects that include the knowledge of the charge transfer. So I don't think that an implicit model by itself has a very good chance of capturing the charge transfer, especially because it's ultimately chemical in nature. But this doesn't mean that it can't be accounted for in some ways for continuum models. Then the second question is about parameterizing continuum models for applications with surfaces, and I guess there are two parts of that. There's different solvents and then different solutes. And for the different solvents, I haven't personally worked with this very much. There is some literature associated with identifying what these parameters would be. Dennis Gunseler's work might be a good reference to look at for considering different solvents. But for the solute side, I don't think that it is very clear how to parameterize solvation models yet, because I think that further development is needed to understand why they're wrong in other instances, right? So we understand the silver 100 pretty well, but we don't know what's happening for other surfaces well enough to know exactly what the next steps are. I know that's a pretty vague answer, but that's where we are now.
I think I have a follow-up question to this, to the charge transfer, which is that could you maybe consider some sort of a hybrid implicit explicit model where the explicit, like a one monolayer of water that can then capture the charge transfer effect?
Yeah. That would definitely be something to consider. The question would also be, of course, how well a single monolayer performs versus, say, a monolayer with AMD. Like, what do you need to know to capture that electron redistribution? Yeah. Is still a very open question. But yeah, that would definitely be one potential strategy.
Yeah. Okay. Because basically this charge distribution comes from some essentially physi or chemisorption of water, right?
Yeah.
And I guess that's what you're getting.
But that might not be the only charge redistribution that's important, of course, is
okay.
Multiple people have mentioned, right? You might have interaction with the electrolyte as well.
Mm-hmm.
Yeah.
Okay. And I mean that in a way like not specific absorption, but rather a charge transfer, of course.
Yes. With say cations. I mean, there's
of course.
of that. Although electrostatics does pretty well, but there is still
there are some exceptions, and I think that of course it depends on what regime you're in, and you have to really know your potential.
So the next question is by someone from DTU. Great presentation. Is the CO gap capacitance result general to all metal surfaces and facets, or is it specific to platinum 111? And is it sensitive to the charge transfer to CO from the metal?
The second question is no. I don't think that as you change the potential, you change the capacitance a lot. I've also looked at this for other systems, and I don't think that it matters as much as you might naively expect, because ultimately you're not changing the electron density in that bond enough to change the capacitance a lot. So how general this is also an open question. And of course, it depends on the electron, the ability of the electrons to redistribute across whatever adsorbate bonds you're considering.
I mean, perhaps I can ask, so when you were first talking about your continuum models, in addition to the capacitance, you also looked at benchmarking to solvation energies.
Mm-hmm.
Can you just give us a bit of, explain a bit what solvation energies you benchmark to?
Yeah, so there are a number of benchmark sets that one can use that include organic molecules and anions and cations solvated in water. And this is important in particular because water has this special feature that that it has a tighter cavity around anions. And this is a source of Shankar's candle model, right? That when the surface is positively charged or neutrally charged, the solute is positively or neutrally charged. The cavity appears to be more or less at the same distance. It requires the same parameters, but this situation changes dramatically with the anions once the hydrogens in water are interacting with the solute.
Yeah.
Does that answer your question?
Yeah, so how do you have some gauge of how well it would perform? So I imagine these solvation energies are kind of like solution properties, but like, do you have a gauge of how well, say, solvation of an adsorbate on a surface would be captured by the model then? So
you have no reason to believe that it would be bad, because molecules are a lot easier than metals. They don't have, for the most part, molecules don't have extreme charge transfer issues. They behave pretty well. The easy way to test, as long as they're neutral, right? If they're neutral, I suspect you'd have no trouble.
Mm-hmm.
If they are charged, then you would need a candle-like model with very specific parameterization, and you'd have to be able to capture that anion asymmetry, right? And I would not say that the majority of solvation models do that well, including ours, because of the strange behavior of anions. But if they were a cation, you'd probably be fine.
Yeah. Thanks.
Yeah. So the next question is from Stefan Ringer, and he says, thanks, Kathleen, for your great presentation. From checking various experimental data, it seems that most metals show a similar Helmholtz and/or a gap capacitance of around 20 microfarad per centimeter square at potentials far from PZC. Do you have some physical explanation for this similarity from your copper platinum study?
So the capacitance becomes pretty low when you get pretty far from the PZC because of a number of reasons, some of which will definitely include the fact that you've now saturated the rotational response of the water. The rotational movement of the water is responsible for the majority of the dielectric constants value. And so once that's all gone, that's really going to limit the capacitance of that element. Now, on top of that, you will eventually, when you're far enough away from the PZC, also run into the nonlinearities associated with the packing. So the ionic limits will also be reached after a point. But these two effects aren't necessarily the only things limiting the capacitance. You might also have other effects, including the distance, the gap region. And the reason that I mentioned the gap region is just because if you have a metal and you're really far away from its PZC, that means that in all likelihood, the electrochemical window isn't large enough to see the metal at the PZC. It's probably covered with something. And this means that you won't be able to eliminate other factors besides the nonlinearity, because you just won't be able to experimentally access it.
Okay.
Okay, so there's another question from Sehong Liu. Thanks for your really interesting presentation. I'm curious about the model you apply in the third part. Do you use a periodic or a flat particle model? And I'm just trying to understand this. And the artificial step between two periodic, are you okay?
Okay, I have an idea. I have an idea.
Yeah.
So of course, when you have a step, you need to have another step in your system to be able to model it. And so you have a number of choices. You could either have a step down surface or one that steps down and up, and in a periodic system. So the first answer is yes, these are all periodic. The second answer is with a neural network, we can actually explore multiple configurations and multiple distances between steps. I didn't show it here, but there also is a step-step interaction. So you need quite large unit cells to get rid of that. And so for those calculations, we are indeed using the step down, step up configuration.
Yeah.
I hope that answers your question.
Yeah. Feel free to follow up in the chat, or of course we can unmute you if you'd like to have a discussion. So
And then there's also one other part, and we also did consider islands as well. But of course, the islands and the CFT results, those are just shown so that you can see the various step configurations, because it's sort of hard to illustrate if you're just looking at a cross section, a near cross section.
Actually, this part is really interesting for us because we work a lot on copper, and sometimes we do have halide electrolytes. So what is the stability of copper in the presence of halides? I mean, if we are using halides in the electrolyte, do you generally expect within a certain potential range there's going to be a lot of dissolution?
Yeah, so it does dissolve at a point. It's fairly stable before that point. The exact potential, I don't know offhand, but people routinely study this surface at potentials near 0 volts versus SHE. And something that has been noted about these surfaces is frizzy steps in STM images. So basically the steps are moving back and forth, and you can see that, but it's too fast to detect on the time scales of STM. So that sort of gives you an idea of how close you are experimentally to an unstable region. And we've also looked at the copper surface with chloride under charge circumstances, and that work will be out soon. So more on that in a bit.
I mean, I don't know, like, actually, do you anticipate that there's effects of charge and solvation? Does adsorb chloride, is it sensitive to you having fields at the interface? Because it looks like your match between theory and experiments is already very good. So
that was sort of a two-part question. The first part is, yeah, they're very charged. I don't think solvation really matters. I think probably disagree with many others on this. The second part is, though, I think that the reason that charge doesn't appear to matter a lot here is because we're looking at surfaces that are fairly well covered across the board with chloride. So we're comparing chloride surfaces against other chloride surfaces. And so to some extent, you're not seeing the potential effects, the effects that you probably would see because of the potential and the higher charge.
Okay, interesting.
And that's probably true of your calculations as well, right? Like we all hope.
Yeah. Yeah, I mean, sometimes it matters, but sometimes we can get away with not doing very much. So
yeah, but specifically, these are highly covered surfaces, and so it's a very nice regime if you're trying to do large scale calculations and you just can't afford the charge, which is the case for us. We wish we could, but And I also don't think that the neural networks are necessarily good enough to capture the long range charge effects.
So there's another question.
From Jeff Lowe. He says, nice presentation. In the last part of your talk, you showed calculations for dissolution from step sites. Did you also consider dissolution from terrace sites? These may not be the most active for dissolution, but I wonder how the energies compare with those on the step edges.
Yeah, so we actually have all of those right here. And you can see that the removal energies are relatively low. I mean, it's true that the removal energy is relatively high. The removal energy is actually lower than that along the step edge itself for non-active sites. So the ordering goes kink site, middle of terrace, and then edge as being the very least favorable. And that is also true for other example shown here. Yeah, all of these atoms were selectively removed, which is one of the benefits of doing a neural network approach. You can just do lots of calculations and it's really inexpensive.
Maybe I mean, if there's no other questions, maybe I can ask like just a very general question about where you think that you can be predictive and where do you think it's a struggle? So you've shown 3 examples. Like, what applications do you think your, say, continuum solvation works well, where you think they don't? Is that too, that's a little bit general, but like.
Yeah, no, but I think that's a very fair question. I think that that's what the community struggles with a lot, because everybody would like to know when I'm actually going to get a good answer. And I think that what needs to be done at this point is very careful benchmarking for the situation that you're interested in. You have to have enough experimental data to know if you're in a good regime or not. So for instance, for the copper system, if you have an idea of what potential you're at and you have an idea of something about the geometry or something about the capacitance, you can see if the continuum model is going to apply there. And if it does, then you can take the insights from the continuum model and actually figure out more about your system. I know that this isn't a very general answer. If you're looking at metals, there's the potential for getting in trouble, not only because of the electron transfer, but also because for a lot of metals, it looks like there's more going on than just a double layer, right? It seems clear that for a number of metal surfaces, even the platinum 111, that you have cations that are explicitly interacting with the surface. And if you're not describing these effects, you're probably not going to be able to describe the surface at all, whether it's with a continuum model or whether it's with full out AIMD.
Yeah. Yeah. So in the data you showed from Cooper, where do you think that your continuum approach breaks down? Because my impression was that it was actually pretty good. So like, what is missing in the picture and here?
Oops.
Yeah.
So this is actually not continuum modeling. This is explicit calculations.
Okay.
And otherwise, you wouldn't be able to capture any of the cation effects. This is strictly an explicit interaction between the cation and the OH.
And a size effect on the field is not going to be able to explain the differences, I guess.
I don't think so.
Okay. That's good to know. No, I mean, I've seen examples from other places for sure where it looks like it's a specific interaction as well. Yeah.
Yeah. You've written about them.
Yeah. Okay. Great. Okay. So if there's no other questions, well, thank you again, Katie, for giving us this really interesting talk. And I think it was really good that you were so basic, because I think that some of us who are not in the field could probably also follow. Yeah, so I hope that the pandemic lightens up and things get better, because I hope I'll be able to see you in person sometime.
That sounds great. Yeah, thank you so much. This was fun.
Yeah, thank you.
Thank you.
Yeah.
See you all then.
Bye-bye.
Bye.